Hi, I'm Mike Seaman with Eta One Power, and today I'll show you how to use Eta Designer's new optimization features to understand the trade-offs in your power converter and optimize your design. In this video, we'll examine the component choices in a 100-watt isolated power module. To start our design, we'll use the new Schematic Wizard. We'll start by entering the input and output specifications, an input voltage from 36 to 72 volts, an output voltage of 3.3 volts, and an output current from 0 up to 30 amps. The maximum output power will then be 100 watts. We'll require an isolated topology. The next step is to choose a topology. We'll choose the isolated half-bridge topology. We'll then set a switching frequency of 300 kHz. Clicking Next and Finish will complete the specification of our design. We'll then modify the schematic to better reflect our target design. We'll set the transformer leakage inductance to 0.5 microhenries. Then we'll set device models for the primary side transistors. Eta Designer provides some filters on the device models based on its simulation results. This filter will include the 100 volt rated transistors in the library. Now we'll choose a reasonable looking transistor, for example, the Fairchild FDMS 86102LZ. Now we'll choose the same model for the other transistor. The next step is to pick models for the secondary side transistors. When selecting the device, we see that the automatic filters overestimate the necessary voltage rating for our device. We'll manually set that to show devices between 20 and 30 volts. Now we'll choose a suitable device, in this case the Infineon MOSFET. Next we'll do the same thing and choose the same device for the other secondary side transistor. Finally, we'll select a model for the output inductor. The filters are set correctly, so we can choose a part easily. Now that our parts are defined, we can run a transient simulation to ensure our converter's control is stable before proceeding to optimize the converter. We see that the output is stable and tracks the input voltage ramp well. If desired, we can further adjust the control loop to improve the startup transient, but this response looks good enough for our purposes. The next step is to optimize the converter. Let's take a look at the features in the Optimize menu. In this menu, we'll be focusing on this section with sweeps and metrics, and the Pareto front and Monte Carlo simulations. The Optimize menu also has a few other features. Snapshots allow you to save versions of your design to recall later, making it easy to judge improvements between versions of the design. The scripting features here allow you to create JavaScripts to perform customizable operations with the design. You can modify design parameters and models, perform simulations and other analyses, perform calculations and custom configuration, and plot the results of your analysis. Scripts are a topic for a future video. We'll start by configuring sweeps for this converter. Sweeps allow you to vary aspects of the circuit over a specified range. We can select between a variable sweep or a device model sweep. Here, we'll create a sweep for the primary side transistor models and select the device model type. We'll then select the desired devices, in this case M1 and M2. The next step is to select the device model options for the sweep. We'll first set up a filter to restrict the model choices to devices with a voltage range between 100 and 200 volts. Now, we'll pick a few transistors with varying RDS(on) to try out in the design. Let's create another sweep for the synchronous rectifier transistor model. We'll call it secondary transistor and choose the device model type. We'll then choose M3 and M4 and then select between models with a voltage rating between 20 and 30 volts. Now that we've defined a few sweeps, it's time to define a few metrics for the converter. Metrics run a circuit simulation and calculate a performance figure of merit for the power converter. We'll first set up a metric to measure the typical efficiency of the converter. The metric is already set up to calculate efficiency, but we want to specify design variables to indicate the typical operating point of the converter. We'll set the typical input voltage to 48 volts and the typical output current to 50% or 15 amps. Next, we want to specify the optimal value of the metric. For efficiency, we would want the highest value. We'll use the aggregation option to pick out the worst case value. In this case, we want the minimum. We'll define a new metric to calculate the worst case power loss of the converter and call it worst case loss. We'll choose the total power loss metric. We'll add specific variables to specify the worst case operating conditions. In this case, maximum input voltage and maximum load. The lowest value will be optimal, and the worst case will be the maximum value. Let's create a third metric to determine the stability of the converter. We'll call it phase margin, and select the phase margin metric under the loop response category. We'll then choose a V-loop filter in our controller, then finish defining the metric. Now, let's take a look at the Pareto front simulation. This simulation will evaluate the circuit at all combinations of the input sweep values. At each combination of the values, it will evaluate the selected metrics, and will then allow the designer to examine the trade-offs in the design and choose the optimal value for each sweep parameter. We'll select both sweeps here to choose transistor models, and we'll select the efficiency and worst case loss metrics to evaluate at each point. Now, we'll click OK, and the simulation will start running. Because a simulation is run for each metric at each permutation of input parameters, this simulation can take a while. Now that the Pareto front simulation has finished running, the results are displayed on a set of axes representing the selected metrics. There are a few points at zero where the simulation of this complex converter failed to converge, but the interesting points are up here. Let's zoom into the relevant points. We have a number of points here, each representing a unique combination of primary and secondary side transistor models. The typical efficiency of each point is on the x-axis, and the worst case power loss is on the y-axis. If we evaluated more than two metrics, we can choose the metrics to plot on each axis here. Now, let's use this tool to examine each specific point. You can hover the cursor over each point to see the sweep value selected and the value of all the metrics, and any simulation warnings that may have occurred. We'll now choose an optimal point and update our devices to reflect this model choice. The primary side transistors are already optimal, but we'll now open each of these devices and choose the optimal model from the Pareto front simulation. Now that we're using the optimal components in our design, we can look at the Monte Carlo simulation. The Monte Carlo simulation will run a sample of simulations, in this case 100 runs. In each run, the simulation will randomly vary the selected parameters, design variables, model parameters, and ideal component values. We'll select model parameters for this simulation and define a normal distribution with a standard deviation of 10%. We'll then select the metrics we want to evaluate at each point, in this case, all three. Now we'll click OK, and then run the simulation. Since we're running 100 simulations and evaluating 3 metrics at each point, this simulation will take a while. We'll fast forward through the simulation. Now that the Monte Carlo simulation is finished, we can take a look at the data. We'll start by taking a look at the phase margin distribution. We have a range from 35 to almost 100 degrees, showing that we have a wide range in stability of the converter. We may want to modify the controller to ensure better stability over parameter variation. Next, we'll take a look at other metrics. The typical efficiency shows a distribution between 95.3 and 96.7%. You'll have to ensure that this range will meet your product specification. Finally, let's look at the worst-case loss distribution. While the average is 5.67 watts, the maximum is up to 6.5 watts. In this design, we would have to ensure that the thermal solution is sufficient for this worst-case loss or variation. In conclusion, Eta Designer has a set of tools, including sweeps and metrics, which help designers choose optimal devices and understand the trade-offs in their designs. I hope you've enjoyed this video and have learned how to use Eta Designer to design and optimize your power converter projects. Please check us out at etadesigner.com to download a trial version and to view more videos like this one. Thanks.